Good morning, everybody. Morning, Michael. It's a new week, new day. How many of you guys just wake up before class? Nine a.m. It's an acceptable time, in my opinion. Any time, really. Just get sleep. That's really the point. How are you guys surviving? It's week 4. Figuring out a schedule, a pattern. When's your guys' first set of midterms? Squiddy, barely. This Thursday. Someone this. No. Daniel, no, not midterm. That's probably for a different class. Email me if you have a grading question. So some of you guys are barely surviving. Are you taking time to do something for yourself, to breathe? 306, is that linear algebra? Or differential equations? Or something completely different? Diffie Q. Diffie Q. If you can make it past Calc 2, I think you can make it past most other math classes. Calc 2 is pretty intense for all of you guys who are in Calc 2. Any questions on the material in this class? Anything I can clarify? Help you guys out? Hopefully you find this class manageable. I know this week was a little long with the Xi books. It will not be that long in the future. Remember, you do not need to do all of the challenge activities. You don't need to do the challenge activities in 3.8, 4.2, 4.5, and 4.6 or something like that. I rage quit the snowfall. What's the snowfall challenge activity? Oh, that one. Okay. So sometimes it helps to really pull out an example, like on paper, what is really happening. So I think 4 is the snowfall challenge activity. No, computer, stay awake. Okay. Okay, it's 4.4.1. Let me help you out for a little bit. Just as a fun aside. So it helps to go through an example. So we have, ignore all the notes on everything, everywhere else. So we have state snow record that looks like this. And we have row num is 2. And then we want city snow record to look like this. And so if you notice, city snow record is these numbers. It's the second row of state snow record. So city snow record is going to be state snow record. Not all of it though, part of it. So I have open close parentheses. And if I want it to be the second row, I would say row 2, and then all of my columns. So this means row 2. This means all columns. There you go. This is it. Except keep in mind that it's not always going to be row 2. It might be a different row. So there's a variable you should use here instead. So sometimes it helps just to go through an example, write it down on paper, go through a different example, make up your own. But just remember, this left-hand side, where do we want to store things? I want to store something in city snow record. What do I want to store there? I want to store the second row of state snow record. Okay. Let's go ahead and begin class. So, welcome to class. Welcome to class. Welcome. Let me get all of my ducks in a row. So, last week, Nicole asked to go over the questions from week 3 videos, and I just didn't. I ran out of time, so I wanted to go over them today. Sorry about that, Nicole. I realized that, like, on Saturday. I was like, I didn't go over that. So I wanted to step through the questions from week 3. So the last week's comprehension quiz. So for a question like this, match the MATLAB code to the type of array it creates, we need to be really careful about what we are trying to do. So for this question, keep in mind, commas put things next to each other, semicolons stack things on top of each other. So for A, 5 next to 3, next to 2, next to 0, that's a row vector. For B, 24.6, that's a single value. It's a scalar. We've been working with scalars since the beginning. It's just one single number, so that's C. For this one, we've got the colon operator here. So this, if I just did 10 colon -1 colon -10, that means I'm starting at 10. 10 minus 1 is 9, minus 1 is 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1, then 0, then -1, -2, etc., all the way to -10. This, by default, creates a row vector. So if I just had this here, it would be a row vector. But I don't have that, I also have this transpose. I don't have just that, I also have the transpose. So what this transpose does is it's going to convert this row into a column. And so all together, I create a row, I transpose it to get a column. For D here, this creates, once again, starts with 0, then 5, then 10. Here, it's 10, then 5, then 0. So here I have a row of 3 values on top of a row of 3 values. Keep in mind, the semicolon stacks things on top of each other. Okay, so this is going to give me a matrix. E here, 9 on top of a 3, on top of a 6, on top of a 1, on top of a 0. So that's a column. And then linspace does the same thing that the colon operator does. It gives me a row vector. Question 2 asks, which of these statements will result in an error? So M equals, so here I have a new vector where I'm going to put 0's 3, 2 next to 1's 3, 5. So this creates a 3 by 2 matrix with 3 rows, 2 columns. This creates a 3 by 5 matrix with 3 rows, 5 columns. So I'm going to put this one next to this one because I have my comma here. When you put things next to each other, they need to have the same number of rows. So this one has 3 rows, this one has 3 rows, we're good. This one will not give me an error. The second one. So here I have a column of 3 values next to another column of 3 values next to another column of 3 values. So here's a 3 by 1, a 3 by 1, and a 3 by 1. They're placed next to each other. Same thing. If you place things next to each other, they need to have the same number of rows. This has 3 rows, this has 3 rows, this has 3 rows. So we're good. For the third one here, I have I4 creates a 4 by 4. 1's 3 creates a 3 by 3. I am putting them on top of each other. So I4 on top of 1's 3. If we put things next to each other, they need to have the same number of rows. If we put things on top of each other, they need to have the same number of columns. So I here has 4 columns, 1's here has 4 columns. So here's where I'm going to have my error. It's going to say I4 cannot be stacked on 1's 3. It'll tell you dimension mismatch, something to deal with concatenation, some error. Okay? Because I can't put something with 4 columns on top of something with 3 columns. They need to have the same number of columns. It needs to end up with something square. And then this last one, this is an alternative way to create matrices. I like to use this method when I have a big matrix that's full of a bunch of values I need to type in. We'll see an example of that on Wednesday. But here I have a row on top of a row on top of a row. If I'm placing things on top of each other, they need to have the same number of columns. So this one has 4 columns, 4 columns, 4 columns, so we're good. So here's my error. For this one, which statement matches the following description? Store a value of 10 in the third row of matrix A. Store a value. That means we're talking about an equals sign. Equals is assignment. It means store a number, store something inside of a variable. Store a value of 10. That means 10 goes on my right-hand side. What am I storing there? 10. So 10 needs to be on the right, so I can't do this one. This one is invalid. Can't do it. Where am I going to store 10? In the third row of matrix A. So the third row of matrix A is on my left-hand side. Where am I going to store things? Remember, left-hand side is where I'm going to store them. Right-hand side, what am I going to store there? In order to access the third row of matrix A, I can do it a couple ways. I could say A3, comma, and then the number of columns, however that is, like this. However, I don't know how big A is, so I can't say 1 through 5, because what if A has 7 columns? I can't do this one because 3 is just the third number. So it's got to be this one. Row 3, all columns. And lastly, which statement is incorrect given the following lines of code? M is 0's 4 by 4. It turns out that's all you need to know. These are just, you can copy and paste that into MATLAB in order to see what your final result is. But really all we need to know is that M is going to be a 4 by 4 matrix. And then I'm looking at a bunch of different functions. The numal function is the number of elements in my matrix. So numal M gives me a 16 because there's 4 by 4, so there's 16 elements in my matrix. Length, the length function gives me the larger of my 2 dimensions. So if M is a 4 by 4, the largest of those is 4. So this one's correct. The size function, I can use it one of 4 ways, the 4 main ways. This way is going to take the number of rows in M and store it in a variable R, and the number of columns in M and store it in a variable C. So I end up with 2 different variables, one that stores the rows, one that stores the column. So here's where it's incorrect because this does not return a 2-element row vector. It returns 2 variables, one with the number of rows, one with the number of columns. And then ndims gives me the number of dimensions, which is 2 because it's a 2D array. Number of rows, number of columns, rows and columns. So here's my answer for that one. Okay, like I said, someone asked me to do that last week. I didn't get to it. Hopefully some of that made sense. If you need any clarification, let me know. So we're getting to the point in our class where we need to start being super careful about what we're trying to do. So this week we are covering matrix math, which some of it is intuitive, some of it isn't. But we're covering a bunch of ways in order to do math with matrices now. We've done it with scalars, and that makes sense. It's just a lot of you guys just keeping track of your parentheses, making sure you use asterisk for multiplication. And Asterose, however you'd say that username. It's not necessarily a difficult spike yet. We will definitely hit a difficulty spike when we get to loops. It's more of a debugging. Like it's more of how careful you are with your debugging. If you are careful about how you write out your code and you're a little more aware of what's happening like on paper and how it's translating, then it's not as much of an issue. But notice when we got to arrays, there's multiple ways we can do things. So now we have parentheses when we're trying to send information to a function. But we also have parentheses when we are indexing an array. Someone mentioned in Discord about the end keyword. So now I can use end inside of my index. I can also use end outside of my index, but those are two different ends. So it's one of those where you just have to be aware of everything that's going on. And it gets more difficult when we get to math because MATLAB stands for Matrix Laboratory. The inherent language of MATLAB is matrix algebra. And there's some differences between matrix algebra and scalar algebra, which is what we are used to. So we're starting to get into some of those nuances this week. Okay. Let's go. Okay, so I've got a bunch of matrices here, A, B, C. A is a 2x3. It has 2 rows, 3 columns. B is a 3x2. It has 3 rows, 2 columns. And C is a 3x3. And I'm going to do a bunch of math operations with these 3 matrices. So first, A plus B transpose. So when we add 2 matrices together, it's going to do it element by element. So A is a 2x3. B transpose is a 2x3. So my result is also going to be a 2x3, where I take the first number in A, the first number in B transpose, add those together to give me my first number and my results. So 3 plus 2 is 5. Keep going. 2 plus 3 is 5. 4 plus 2 is 6. And then the second column gives me 8, -6, and 1. That's pretty straightforward. Matrix addition makes sense to most students. If I had a 2x3 plus a 3x3, I can't do this. My dimensions need to match. I need to have the same number of rows as I do columns. So I have a mismatch in dimensions. Something like that in MATLAB will give you an error. However, if I have a matrix plus a scalar, what it's going to do is here I have a 3x2. My result is also going to be a 3x2. Where it's going to take the scalar and add it to every single number in my matrix. It doesn't matter the order. It could be the scalar plus the matrix. It doesn't matter. Where 2 plus 2 is 4, 3 plus 2 is 5, 2 plus 2 is 4, and then other side, 5, 1, and -2. Remember to add, not multiply. Those are rules for addition. It matches your intuition. It matches more or less what you would think for scalar math. Same thing for subtraction. Same thing, if I have a 3x2 minus a 3x2, my matrix result is going to be the same, where first number, 2 minus 3 is -1, 3 minus 2 is 1, 2 minus 4 is -2, 3 minus 5, -2, and then 4 and -1. Element by element. Take the first element in my first matrix, subtract the first element in my second matrix to give me the first element in my result. Same thing for subtraction as it is for addition. If I have a 3x3 and a 3x2, I can't do that. I need to have the same number of elements, the same orientation, same size, same number of rows, same number of columns. Keep in mind, MATLAB will do some funky things. So if I go over to MATLAB, there we go. If I go over to MATLAB, so here's my A, B, and C, and I try to do C minus B, it will give me an error. It will tell me matrix dimensions must agree. However, if I do C minus a row vector, 1 through 3, see, I don't even know what happened there. But if we do something like this, MATLAB's not going to give you an error. It's going to give you something funky that it did. And what I think it did is I think it minus 1, minus 2. I don't even know. So here's an instance where MATLAB isn't always necessarily going to behave exactly the way we expect it to on paper. So we need to be careful about what we're trying to do. I tried to subtract 1, 2, 3. And in theory, I should get an error. C is a 3 by 3. This is a vector. So I should get a matrix dimension must agree. But MATLAB's not always going to behave exactly the way we think it's going to in instances like this. So it's really careful that you understand what you're trying to do and how to correct for it. So here, if we're trying to subtract something from each column, it would be clearer if we created another matrix that we can subtract element by element explicitly. And like I said, I'm not quite sure what MATLAB did here. Didn't behave the way I think it was going to. So sometimes you just kind of need to notice, okay, MATLAB isn't doing what I expected it to. Go back, change it to be explicitly of what you think is going to happen on paper. So like I said, we're starting to get to this area where you can get in trouble because you don't necessarily understand what MATLAB is doing. That's why I'm really strong advocate of the highlight, right click, evaluate selection. It will help clarify things. So I meant to do this, and this I understand what it did. It copied this, it subtracted this vector from each column. So this one I understand. This one I do not. Okay, let's go back to notes. If I subtract a scalar from a matrix, so once again, it doesn't matter the order of these. Same thing is going to do it element by element. So if I have a 2 by 3 minus 4, it's going to create my final result. It's going to be a 2 by 3, and I'm going to take this 3 minus 4, negative 1, 2 minus 4, negative 2, 4 minus 4, 0, 5 minus 4, 1, and then negative 9 and 1. So it's going to be element by element. Addition and subtraction matches our intuition. It matches what we expect to happen when it comes to matrix math. Okay, next one, multiplication. Multiplication is where we start to deviate. It's not as straightforward. Scalar, though, if I have a scalar times a matrix, this one's straightforward. Same thing with addition and subtraction. We're just going to multiply that number by every element in our array. So if my array is a 2 by 3, my result is going to be a 2 by 3, where I'm just going to take 3 times 3, which is 9, 3 times 2, 6, then 12, then here 15, negative 15, and 15. Okay? That one's straightforward. So Pat Fallon, so dimension mismatches only happen when two matrices have different number of columns. Not necessarily. They can have different number of rows. So if I go back to MATLAB, C looks like the A. There we go. A has 2 rows. If I try to do C plus A, it will give me a matrix dimension must agree. So it depends on your operation. So in your addition, in theory, MATLAB should give you an error if A and C don't have the same number of rows and the same number of columns. So both need to match. Like I said, there is a gray area on what happens when you have a matrix plus a vector that does some wonky things in the background. But that's what happens when we have matrix dimension must agree. It means the number of rows and the number of columns, however it is, don't match what is expected for the operation. For addition and subtraction, it needs to be the same number of rows and the same number of columns. Okay, so that is scalar multiplication. That one also relatively straightforward. It makes sense. Let's talk about matrix multiplication. Let's say I have A times B. This is going to follow the matrix multiplication rules. Matrix multiplication is a series of dot products. It's a series of dot products. So it does not follow essentially pretty much anything you've really ever been taught before. You may have seen matrix multiplication in high school. Most of the time, students have not seen it at all. So matrix multiplication rules, essentially we can perform matrix multiplication. We can do A times B as long as the number of columns in my first matrix matches the number of rows in my second matrix. So this is what I was talking about in the video. Okay, so here we have an example over here. So here, A is a 2 by 3, and B is a 3 by 2. So here, the number of columns in A matches the number of rows in B. So in Physics 107, you're learning this last week, according to small groups, you're learning vectors and cross products. I don't know how much you get into matrix math. The cross product is related to the determinant, but I wouldn't necessarily say that what you learned in Physics 107 is necessarily exactly the same as this. But yes, you did learn about dot products in physics. Good connection. I like it. Thank you, real Eddie Murphy, for real. Okay, so the number of columns in A matches the number of rows in B, so that's great. Our result is going to be an entirely new sized matrix with the same number of rows in A and the same number of columns in B. So here my result is going to be a 2 by 2. I'm going to move this. Some music today is so weird. Okay, so my result is going to be a 2 by 2 matrix. I'll make it nice and big. So when you have a matrix, a 2 by 2, I have 4 locations that exist in a 2 by 2 matrix, right? I have first row, first column. I have first row, second column, second row, first column, and then second row, second column. So I have 4 locations. We are going to identify what numbers we're going to get here by doing a bunch of dot products. And those dot products are going to be between the rows in A and the columns in B. So if I want to find what this number is supposed to be, in my first row, first column, I'm going to do the dot product between the first row in A and the first column in B. So row 1, column 1, take row 1, column 1. The dot product, so let's go review the dot product. Since you just learned it in physics, all of you guys should know exactly how to do it. But the dot product is pretty easy. The dot product is between 2 vectors. So dot product between 2 vectors of the same length. So they need to have the same number of elements. What we're going to do is we're going to take the elements in my first vector, multiply them by the elements in my second vector, and add all together. So if this is my first vector and this is my second vector, note I wrote them as a row and a column. It doesn't matter if they're rows or columns. The only thing that matters is if they have the same number of elements. So I'm going to take 3 times 2. Plus 2 times 3, plus 4 times 2. And I do that. I add it all together. So 6 plus 8, which is 20. Okay, same thing here. If I did this one, take the elements in my first one, multiply by the elements in my second one, add them all together. So -1 times 3, plus 3 times -1, plus -1 times -4. Do the math. -3 minus 3 plus 4 would be -2. Yeah. So that's the dot product. You just take the elements in your first vector, multiply them by the corresponding elements in your second vector, and add it all together. When we do matrix multiplication, we are doing the dot product over and 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 over again. So here, my example for A times B, I have a 2 by 3 times a 3 by 2. My result is going to be a 2 by 2, which means I need to do 4 dot products, 1 per location. The dot products are going to be between the rows in A and the columns in B. For my first number here, it's a dot product between row 1, column 1. So 3 times 2 plus 2 times 3 plus 4 times 2. That's 6 plus 8, that's 20. We actually did that one up there. So this number here is 20. If I wanted to find this number here, I'm going to take row 1 and column 2 because it's in row 1, column 2. So it's going to be 3 times 3 plus 2 times -1 plus 4 times -4. Or 9 minus 2 minus 16, or -9. Same thing. For this one, I'm going to take row 2, column 1, because it's in row 2, column 1. Dot product. 5 times 2 plus -5 times 3 plus 5 times -4. Nope, wrong one. Times 2. So 10 plus 10 minus 15, 5. And then last one. So this number here, I'm going to take row 2, column 2, because it's in row 2, column 2. So it's going to be 5 times 3 plus -5 times -1 plus 5 times -4. Or 15 plus 5 minus 20, which is 0. So there we go. There's my answer. 4 locations, 4 dot products. Rows in A, columns in B. Okay, so that's A times B. Let's look at B times A. B times A. It's going to be different. Don't know why I did that. So B is a 3 by 2. A is a 2 by 3. So notice these inner dimensions match. The number of rows and the number of columns in B matches the number of rows in A. My result is going to be the outer dimensions. It's going to be a 3 by 3. So A times B was a 2 by 2, as illustrated here. B times A, though, is a 3 by 3. A 3 by 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 locations. That means I need to do 9 dot products. It's a lot more. So the order matters. A times B is not equal to B times A. Okay, order matters. So in order to find this one, first row, first column, 2 times 3 plus 3 times 5 gives me 6 plus 15, 21. This number, I'm going out of order for fun, because it doesn't matter. It doesn't matter. You should be able to identify what the value is going to be regardless of where it's located. This is in row 2, column 2, so I'm going to take row 2, column 2. 3 times 2 minus plus -1 times -5, or 6 plus 5, which is 11. Now let's take this one. This is in row 1, column 3. So I'm going to take row 1, column 3, dot product. Are you talking about for A times B? It should be -9. I'll ask MATLAB. Nope, it's -9. So you can always check your answers with MATLAB. If I just do A times B, this is the normal asterisk, A times B, it will do the matrix multiplication. So A here is my 2×3, B is my 3×2, my result was a 2×2, it does the dot products. So you can always check your answer with MATLAB. So -9. Back to notes. So for this one here, it's in row 1, column 3, so I take row 1, column 3, dot product. 2 times 4 plus 3 times 5. So 8 plus 15, 23. I can do basic math. And you would just keep going. Sometimes it really helps to show all of the math, how it all works out. I like to sometimes write out all the dot products. So let me erase this. And write them all in one big matrix. So it would be 2 times 3 plus 3 times 5. So row 1, column 1. And then row 2, column 1, so 3 times 3 plus -1 times 5. And then 2 times 3 plus 4 times 5. Sometimes it helps to write it out like this. You'll see the patterns. Note 2, 3, 2. It's 2, 3, 2. That's my first column. 3, -1, 4. 3, -1, 4. That's my first column. 3, 5, 3, 5, 3, 5. That's my first column here. Second column here. 2 times 2 plus 3 times -5. 3 times 2 plus -1 times -5. 2 times 2 plus 4 times -5. Same idea. You'll notice patterns. 2, 3, 2, 3, -1, 4. That's this matrix. 2, -5, 2, -5, and all that. So you'll notice patterns. It's important that you guys understand what's happening behind the scenes. But sometimes I like to write it out like this, just to note the patterns that is going on. You will get practice. You will get better. So 2 times 4 plus 3 times 5. 3 times 4 plus -1 times 5. 2 times 4 plus 4 times 5. And then you would do all the math. Okay, let's look at this last example, C times A. C is a 3×3. A here is a 2×3. So notice 3, 2. These dimensions do not agree. This number of rows, or the number of columns in C does not match the number of rows. And you can notice that makes sense because when we do the dot product, I'm going to take this one and this one. Those don't have the same number of elements. Those don't have the same number, so you can't do the dot product between this. So this is invalid. This will give you a dimension mismatch. If we go to MATLAB and we try to do C times A, you will get a bigger error. It will tell you incorrect dimensions for matrix multiplication. It tells you it's trying to do matrix multiplication. However, in order to do the matrix multiplication, the number of columns in the first matrix must match the number of rows in the second matrix. So, Michael, that's a really good question. That is not... You can't assume that because these numbers in your matrix usually correspond to something. They usually correspond to coordinates or some actual data. And so you can't just add zeros and just say, oh, I just assume it's zeros. If you want it to do that, you can explicitly program it to do that. But you have to do that because the default behavior is not to do that. Because it really depends on your application. Good question. Okay, how are you guys feeling with matrix multiplication? Do you want me to go over another example? Can we keep going forward? Thoughts? I went over another example this morning, so if someone says yes, it's not like you shouldn't feel like, oh, all of this makes sense and I'm just an idiot and I can't understand it. I'll save you guys. I'll go over another example. Let me do a 2 by 2. Let me do it over here. So let's say I have a matrix 3, 0, -1, 1, and I want to multiply it by another matrix 2, 4, 5, -2. Okay, first thing you need to do, check your dimensions. 2 by 2, 2 by 2. 2 matches the 2. Check. Woohoo, we're good. My result is going to be these outer dimensions. It's going to be a 2 by 2. Means I have 4 dot products to calculate. This first one, first row, first column. First row, first column. 3 times 2 plus 0 times 5. That's going to give me a 6. Then I can do whatever other number I want. Let's do this one. Second row, second column. Second row, second column. -1 times 4 plus 1 times 2. That gives me -4 plus 2, -2. I can do any other one I want. Let's do this one here. First row, second column. First row, second column. 3 times 4 plus 0 times -2, or 12. And then last one here, second row, first column. Good. So I'm going to take the second row, first column. So -1 times 2 plus 1 times 5, or -2 plus 5, 3. There we go. There's my result. If I change the order, I would still get a 2 by 2. It would be different. The numbers would be different, or at least in a different order. Okay, that is matrix multiplication. That is the default behavior when you use the asterisk. Okay, you need to remember this. Okay, MATLAB, however, gives us an alternative. If we do not want to do matrix multiplication, let's say we want to do multiplication pretty much similar to how we do addition and subtraction. We wanted to do element by element. MATLAB gives us an alternative with the dot notation. Oops, wrong one. Where if we type dot asterisk, what this means is this is going to do element by element. Where it's going to take the elements in our first matrix, multiply them by the corresponding elements in our second matrix. The same way we did addition, same way we did subtraction. So note, if I have C dot star B or dot asterisk B, here I have a 3 by 3, here I have a 3 by 2. If I wanted to do regular matrix math, this would work. If I just did C asterisk B, it would give me a 3 by 2. I don't have a regular asterisk though, I have a dot here. So a dot indicates that I want to do element by element. When we do element by element, the dimensions need to match. So this is not possible because my dimensions do not match. So I can do C asterisk B, that's good, but I cannot do C dot asterisk B, that's bad. So keep in mind what you're trying to do. This is what I mean by where we might run into issues if we don't really fully understand what we're trying to do behind the scenes. What is happening? How big are my variables? What do they store? Are they arrays? Are they vectors? Are they matrices? Are they scalars? So we need to understand what we're talking about. So if I did A transpose dot asterisk B, here we go. We have a 3 by 2, a 3 by 2. My result is going to be 3 by 2. Where it's 3 times 2, which is 6, 5 times 3, which is 15, 2 times 3, which is 6, -5 times 1, -5, 4 times 2, 8, and 5 times -4, -20. So this dot makes all the difference in the world. Pat Fallon, C times A can't be done because the dimensions don't match. So C times A, C is a 3 by 3, A is a 2 by 3. Without the dot there, it's matrix math. So the number of columns in C must match the number of rows in A. That doesn't happen, so you can't do this. You can't do this. It's just not possible. MATLAB will give you an error. Incorrect dimensions in matrix multiplication. Okay, so like I said, this asterisk here is matrix multiplication. Number of rows, number of columns in A must match the number of rows in B. The dot asterisk is element by element multiplication. Yes, Sophia, it would have worked if it was a 3 by 2 and a 2 by 3. Yep, absolutely. Okay, so a couple things to note when it comes to operations. So if I have C squared, and C is a matrix, this is essentially the same as saying C times C. So remember, it's C times C matrix math. So it's literally taking -5, -1, -1, 3, 3, -3, and multiplying it by itself. This is going to be matrix math, or matrix multiplication, where my result is going to be a 3 by 3, and it's going to do all those dot products. If we look at MATLAB, C squared, it gives me this. It works. But note, you might think that it's going to be each element inside of C squared. So you think it might be 25, 1, 1, 9, 9, -9. It's not that. It's C times C. It's as if we type C times C, where it does the dot product between the rows in C and the columns in C. Okay, so you need to be very careful about what you're trying to do. So it is possible to raise a matrix to a power, like C squared, C raised to a power. However, this must be a square matrix. And keep in mind, you're doing C times C times C times C n times. If we want to do each element inside of C squared, we can use our dot notation. So MATLAB allows for, sorry if I'm giving you guys a headache, but MATLAB allows for element by element multiplication. It also allows for element by element exponentiation. Pat Fallon, I will get to your question. So over here, I have C dot squared. This one's much easier to calculate. We are just going to take each element inside of C and square it. So -5 squared, 1 squared, 1 squared, 3 squared, 3 squared, -3 squared, 0 squared, 1 squared, and 2 squared. So the difference between these two, this one is only possible with square matrices, and it's going to be C times C times C times C following matrix multiplication. This one, with my dot, is just going to take every element inside of my matrix and square it individually. Okay. So Pat, let me do it over here. So Pat, C times B. C is a 3 by 3. B is a 3 by 2. That completely works. This works. That's great. C times A is a 3 by 3 and a 2 by 3. This does not work because 3 does not match 2. B times A, B is a 3 by 2, And A is a 2 by 3. This works. It gives me a 3 by 3. A times B is a 2 by 3 and a 3 by 2. This works. This gives me a 2 by 2. So you just need to check the dimensions. You just need to check if these inner dimensions match or don't match. If they match, you're good. You'll get a result. You won't run into any errors. If they don't match, you won't. They don't work. Okay. So let me get in some final details, some final caveats in the last 5 minutes here. So typically what we want to do in MATLAB, a lot of times we want to do element by element applications. So for element by element operations, they need to be the same size. So for element by element, they need to have the same number of rows and columns. Okay. So you need to keep track of what you're trying to do. Are you trying to do matrix multiplication? In which case, you need to check these dimensions like I just mentioned here. Are you trying to do element by element? Then you need to make sure they're the same size. So for example, we might see something like this, where we're going to have a vector, square divided by a vector times a vector. And you've seen this notation. Essentially, it's a squared divided by b times c. This is our scalar notation that we've seen previously. But what if a, b, and c aren't scalars? If a, b, and c aren't scalars, then it's going to apply the rules of matrix math, of matrix multiplication. So it's going to say a times a, assuming matrix multiplication. It's going to do that result divided by b. We haven't talked about what divide means when it comes to matrices yet. We will talk about that on Wednesday. But it's a form of matrix multiplication. Same thing, b times c, it assumes matrix multiplication. So if we have vectors like this, we're going to run into some problems. If we have a 6 by 1, we can't multiply it by a 6 by 1. These dimensions don't agree. And a lot of times we don't want to do that. So what we need to do is we need to use our element by element notation, which might look something like this, where we put a period in front of all of our operations. And that's good, that's great. However, keep in mind, you might run into some funny you might run into some funny issues if you have row vectors combined with column vectors. So here I have a column, here I have a column, and here I have a row. In MATLAB, that gives me this. It gives me a whole matrix where here's my row, or here's my column, here's another column, but this last one here is a row. You might expect it would give me a single column. However, MATLAB, it doesn't behave that way. It gives me this for some odd, obscure reason. So here's another unexpected behavior where there's no error, but it doesn't quite behave the way we expect it to behave. So when we're doing element by element operations, make sure everything is explicitly the same size, or MATLAB might give you some unexpected behavior. So if I have this column squared divided by this column times this column, element by element, so here I have my periods in front of everything. What this is going to do is it's going to take this 3, it's going to square it, divided by this 2 times this 5. And then do that with the second number. So 5 squared divided by 3 times -1. Third number, 2 squared divided by 2 times -1. And then keep going. And a lot of times we want to do this in MATLAB. For example, I'll go through this example and then we'll be done. For example, let's say we want to do a bunch of calculations across, a bunch of the same calculations across a bunch of numbers. So here I have x that looks like this, It's 0.5 colon 0.5 colon 2.5, and y that looks like this, 0.8 colon 0.8 colon 4. And now I want to calculate z for all of these x and y values. In this instance, I'm not doing matrix math. I don't want to do matrix multiplication. I want to literally take these first set of numbers, do the calculation, these second set of numbers, do the calculation, etc. So here's my strategy for you guys. If you are planning on doing element by element operations, what I encourage you guys to do is first type it out as if it was just all scalars, just like you did in week 1. So x times y times exp, y divided by x minus nth root x raised to the 4 times y cubed plus 8.5 comma 3. Right? Write it out as if it was just scalars. And then go through and change it so that all of my operations, change my asterisk, my division, and my caret for exponentiation to my element by element. That's his element by element, just ignore it. To my element by element operations. So put a period in front of all the asterisks, and put a period in front of all the division signs, and then put a period in front of all of your exponents. This will then ensure that if x and y are vectors of the same length, it will do element by element operations versus giving you an error that says, hey, your dimensions don't match because you're trying to do matrix multiplication. Okay? So that's it for today. We went over a lot. We went over addition, subtraction, matrix multiplication, element by element operations. That's a lot. On Wednesday, we are going to go over division and solving systems of equations, which is something you're going to do a lot in this class. So with that, any final questions? Hopefully some of this made sense. As you practice, you will get used to things. But it's important that you keep track of what you are trying to do. Element by element operations will always result in a matrix of the same size. Yes. So if everything is the same size, so once again, like I said, keep track of whether or not you're working with rows or columns. It should be all rows or all columns. This z will result in a row vector the same size with 5 locations, where it uses these calculations to do this one. These calculations do this one, this one, this one, and this one. For homework 3 problem 4, what do you mean by not? So that's the square array. So first of all, n can be any number. So if n is 12, then you would be typing 1 12 times, and then you would be doing 2 12 times, and 3 12 times, 4 12 times. But n is 3, then you would only be doing it 3 times. Like, you can't literally account for all of those scenarios. So use your variable n in order to create your subarrays, and not type the numbers explicitly. I mean, anytime you don't have to type them explicitly, you shouldn't, unless there's no other option. Did that make sense? Any other final questions? A lot to take in. Okay, with that, I will see y'all on Wednesday. It's gonna be a great day. Pat, no. If your questions pertain to the lecture, ask them in lecture. If you have questions, probably someone else has questions. So if it is a question that pertains to the lecture, ask during lecture. That is completely perfect. If it's not clear and you don't feel like I'm understanding your question, then maybe just send an email for follow-up or go to office hours. But your questions were completely fine. They were completely fine. I hope I clarified everything. Hopefully it makes sense. Do you still have more questions on it? Okay. Awesome. I'll see you guys on Wednesday. Have a great rest of your week. You can do it. Squiddy, good luck on your exam, and everybody else who is in the Sullivan's DiffyQ class. You can do it. Keep chugging forward one thing at a time.